There, I'll start. CET236, and I'm going to be talking about mesh analysis and nodal analysis.
Professor, you're muted.
I'm muted. Very good. Thank you. Okay, so welcome to CET236 again. We're going to be going through mesh analysis and nodal analysis again. That's what I want to try and get through today. So that's where we are. March 6th, the 6th week, but the 5th lecture because of the President's Day break. And I haven't highlighted anything new on this list. We're going to, like I said, recap on mesh analysis and maybe do a little bit more on nodal analysis, particularly about super nodes. And that's where we are. There's, as I think I told you last week, I've put out all of the things we need to do between now and the end of semester, and that's the homeworks and the labs. There might be one more homework and one more lab about op-amps. But I'll let you know when that's available. So today's session, I want to review mesh analysis. I want to review nodal analysis. Particularly, I want to talk about the super node and super mesh issues. All right. In mesh analysis, we're using Kirchhoff's voltage law, and the nice thing about using Kirchhoff's voltage law, or rather doing mesh analysis, is we're interested in the currents. And the nice thing about having a current source with only one mesh current through it is that we know immediately what that mesh current needs to be. Either it's the same as the current source, or it's the negative of the current source. The problem is when there are two mesh currents flowing through a current source, then we've got a problem, because we can't write down a KVL equation, which is what mesh analysis depends on. We don't know what the voltage drop across a current source is until we've finished the analysis. Similarly, in nodal analysis, if we have a voltage source connected between the reference node and another node, then we know immediately what the node voltage is, right? It's got to be whatever the voltage source is. Again, plus or minus. If the positive terminal of the voltage source is connected to the non-reference node, then the node voltage is just the reference, the voltage source voltage. But if the negative terminal of the voltage source is connected to the non-reference node, then the node voltage is the negative of the voltage source. But I'll go through that a bit more. I'm going to take any questions about Lab 3 and Homework 4. And I've already taken some. I've just responded to a couple of questions about Homework 4. There's a few gotchas in there. One of them is some of the answers require units, and other parts of the answers don't require units. Usually the equations don't require units. Okay. And then Lab 4 is due next week, and I'll do a demonstration of that. We'll see if we can go through that. Any questions so far? Okay, so let's have a look at the let's go back to mesh analysis. Okay, and there's a few examples here that I haven't done, particularly this midterm example, though it's not that different from the other one, right? So let's start with this one, right? So this is a super mesh example, and it's a super mesh example particularly because of this current source, right? We've got I1 going through it, and we've got I2 going through it. And because of that, we can't write a KVL expression, a Kirchhoff's voltage law expression, for the mesh that is I1, and we can't write a Kirchhoff's voltage law equation for the mesh that is I2. Jonathan, I think, can you mute, please? Getting a bit of, or maybe it's, thank you. Also Mel Kumar, can you mute, and maybe Franklin as well? Thank you. So the issue is that this, you cannot say, what I see students doing in this equation, in this situation, is, okay, we've got I1 and we're going into the negative side of VS, so that's minus VS, and then plus I1 R1. And then what I see them doing is just writing it down as plus IS equals 0. And that's wrong, right? Here we've got voltage, here we've got voltage, here we've got current, right? And you cannot add apples and oranges. You've got to have everything in the same units in order to be able to add them. You could write it out as VIS. Let me just change the color. Right? If you could figure out what VIS is, then that would be okay. The voltage drop across IS, that is perfectly okay. But we don't know what that is until we've figured it out, until we've solved the circuit. Right? So try to remember, when you see that arrow in the source, that you can't figure out what the voltage is, what the voltage drop across it is. And here's an example with two current sources, and they've got there's two different cases, right? So the top one, the 4 amp source, that is only has a single mesh current going through it. It only has I1 going through it. So we can write down immediately what the what I1 is, because I1 is going in the same direction as the 4 amp source. That means I1 has to equal 4 amps. But the bottom source, the 5 amp source, we're stuck, right? And we can't write down a KVL equation. We can't write down a KVL equation here, and we can't write down a KVL equation for the I3 mesh either. So what we have to do is we have to, as it says up here, we have to write down a KCL equation that says, okay, I1 is going in the same direction, I2 is going in the same direction as the source, minus I3, because I3 is going in the opposite direction, equals 5 amps. And that's effectively a KCL equation. And then the other thing we need to, because we have two unknowns, so we need two equations.
Professor,
Yeah, what's up?
I2 and I3 is going in the same direction, right?
Nope, they're going in opposite directions through the current source, right? If you follow I2 around, it's going that way, right? And if you follow I3 around, it's going that way. So they're going in opposite directions through.
All right, thank you.
Okay. They're both going clockwise. So in that sense, they're going in the same direction. But as far as the direction that they pass through the current source in, they're going in opposite directions. Okay, so the way my expression for going in the same direction, right? I see the issue, but yeah, I mean if you the both of them are going clockwise, right? Whereas, but the issue is that through that particular component, they're going in opposite directions. Okay, so I thought it might be good to do this last question again, all right? And let me just, before I forget about it, let me just fire up Matlab, and I will use Matlab. I think if I can figure out where it goes, I'm hoping the video isn't too bad today. I'm using a slightly different setup, and it's I wasn't sure that the stream that I'm putting out is quite the same resolution. But anyway, I'll have a look at it on YouTube. In fact, I should. Let me just check the link, and I'll put the link in the where are capstone materials? No, it's 236 materials, isn't it? There we go. So there's the live link, maybe? Yep, there we go. So got my shareable link, and I'll put it in the I've had a couple of people have to not be here today, so that way at least they can see it later on. Okay, looks like Matlab started up. And okay, so remember the sequence of steps, right? So first of all, we define the mesh currents. Okay, and I usually, so be careful, right? In this sort of a question, I have already defined, or the polarity of some things. In fact, let me just do that in a different color. The polarity of some of these have already been defined. So there's Vx, and there's the polarity of V out, right? So you've got to be very careful. My suggestion is that what I mean by being careful is to make sure that you don't define VR2 that way, right? And you don't define VR5 that way. Okay, because if you define the polarities that way, that will mean that Vx is equal to minus VR2 and V out is equal to minus VR5. And that means Ohm's law doesn't apply directly. So it means that Vx will be minus I1 R2 and V out will be minus I2 R5. Okay, so I suggest my suggestion, and the thing I say being careful about, is to try to select the mesh currents so that you keep the passive sign convention on the elements that already have their polarities defined, right? So in this case, it means choosing I1 going that way, right? So there's I1, and that means we're going in there and we're okay there, and we're going in there and we're okay there, okay? Similarly over here, to choosing the current direction correctly as far as the polarity of V out is concerned, we need to choose I2 going that way. And what I might do is I might do the question both ways, right? Let me just see if I can take a copy of that. Okay, so I'll do the question this way first, and then I'll do the question the other way. And I'll show you what I mean by needing to be careful. You could still do it the other way. No problem with that. You just have to be very careful with signs. Here you still got to be careful with signs, but you need to be less careful. Okay, so that was the first one, to find the mesh currents. And then next is we write KVL equations.
Hello.
Yep. What's up?
Real quick, so whatever the voltage source polarity is, the resistance or the resistors are the opposite? Is it always like that?
Well, sort of, yeah, right? So it's a difference between having an active element, like a battery or a current source, and having a passive element, right? A battery is an energy supplier or a power supplier, whereas a passive device like a resistor is a power, what's the word, sapper, or a power, right? It takes power out of the system, whereas an active source. So it sort of is.
I think I get it.
Yeah.
That's a good explanation.
Okay.
Thank you.
You're welcome.
If that's the case, why is I1 clockwise? Because the orientation of that voltage source is opposite from the one of I2.
Right. So there's always a contention between the passive sign convention and keeping the signs correct, and what we know about the way electrons flow, right? Well, and even that's a little confusing, right? We know that from the positive, the current flows that way, right? And from the positive, the current flows that way. Okay? So, but I've chosen I1 to go in the opposite direction of the current from VS1. That's okay. It just means one is the negative of the other. They're going in the opposite direction. I2 is the other way. I2 is going in the, quote, right direction. Okay, so I'm not sure I've answered the question. Can you repeat the question or maybe restate it?
I was asking why we chose that orientation for I1.
Okay, so the whole reason I chose both orientations is for I1 is because we already had that positive sign identified as the polarity of Vx on the circuit before we started. And what I don't want to happen...
Okay, I didn't realize that.
Okay, what I don't want to happen is I don't want to make I1 go into the negative side of Vx if I can possibly avoid it. Okay, because otherwise, if I do that, then I need to use the anti-passive sign convention version of Ohm's law, which is V equals minus IR, which confuses everybody, including me.
Gotcha.
Okay. So I am going to do it the other way, but I'll show you. Let's do it this way first, which I think is a little less confusing, and then I'll do it the other way and show you where the confusions can happen. Okay, so we need to write KVL equations. So on the blue side of the loop, we're going into the positive side of the voltage source, and then we've got VR1 and then plus VR2, and in this case VR2 equals Vx, right? We're using the same polarities, and then plus VR3 equals 0. So that's our KVL equation for I1, and then we can do a KVL equation for I2. Now I2 has a minus 5 Vx, and note the X, right? This is not 5 volts. Right? Vx is defined up here. Okay, so it's minus 5 Vx and then plus VR5 plus VR4 plus VR3 equals 0. And I did something I shouldn't do. I forgot to put polarities on the I2 loop. Okay, so there's our KVL equations. The third step is to write or replace voltages with the IR, so use Ohm's law. Okay.
When you ask for the KVL equations on the homework, do you want them in terms of like VR5, VR4, or do you want it to be written out?
No. So the KVL equations in the homework unfortunately require the only valid variables in web work are the currents in the case for mesh analysis. Okay.
Okay.
So you'll need to write it out on the equations you get after step 3 in what I'm doing now. Okay, so there we go. We've got 12, and VR1 is, now it's another thing. Note the K there, right? We have to have 6800 I1, and then VR2 is 2200 I1, and then R3 has I1 plus I2 going through it, so it's going to be plus 4700 I1 plus I2, and that's equal to 0. And then we can sort of write that out, so that's 8,800, 9,000, 13,700 I1 plus 4,700 I2 equals minus 12, right? Because we've got to take the 12 over the other side. And then now minus 5 Vx, because of the way we've defined Vx, it's just minus 5 times 2200 I1, right? No calamities. And then plus VR5 is again no calamities. We're all aligned polarity wise, so that's going to be 4700 I2, and then let's just scroll across a bit so you can see it, and then plus 8100 I2, and then plus 4700, and it's I1 plus I2, or I2 plus I1, doesn't really matter, and that equals 0. Then pulling all of that out, what's that? That's 11,000 I1 minus 11,000 I1. So what's that? That's minus 6,300 I1. Have I got that right? And then I2, it's 12,800, 16,800, 17,500. And that equals 0. Haven't quite got everything on there. Okay, so now we can write our RF equation, right? It's going to be 13,700, 4,700 minus 12 minus 6,300, 17,500 and 0. Okay, now let's just pull up Matlab. Oops, it's over there. Let's move it over here so I can still see everything. So this is oh, why does it do that? It, for some reason, now it's okay. Now it's letting me type again. It wasn't letting me type. I don't know why it does that. So we just put that in, and then minus 6,300, 17,500, 0. Just check that that's right. 3,700, 4,700, 6,300, 17. Yep, that looks good. And then we just use the RF function. And I'm just going to put that into A1 and then look at A1 1,3 times 1,000 maybe. Right, so it's minus 7 point. Let's do it that way. There we go. So there's so that tells us that let me just see if I can move that over there so I can write it down here. So that means our answer comes out as I1 I2 equals minus 0.7794.
Professor.
Yeah.
Can you explain that last step with the matrix? Because I thought we just had to use RF.
I did just use RF. Oh, which last step?
The A113, I wasn't sure what that operation was in
Okay,
Map.
so what I did is I put the result of the RF operation into A1, and the trouble is it'll print it out, but then I can't see more than one significant figure. Okay, so what I wanted to do,
Oh,
this is just saying give me the full column at give me the all rows at column 3 and multiply it by 1,000. That way I can see 4 significant figures.
okay, thank you.
Okay, no worries. That's all right. Yeah, no, I dread to think how long I've been using Matlab. So it's just muscle memory at this stage. So I get that people aren't as familiar with it, but I forget. Sorry. Okay, so and that's that in milliamps. Now remember what I said about the green current directions, right? And you can see that at least for I1, that is the right current direction, right? I1 is actually going in that green direction. Trouble is, the current out of VS2 is actually going that way. Right? So you've got to be really careful with what your intuition tells you about current flow direction. The reason it's not flowing in what I wrote, the green direction that I wrote before, this one here, is because this source is probably overpowering it in terms of where the current is flowing. And so you're probably not going to get what you think in terms of current direction. Okay, so that gives us one answer. I'm going to do exactly the same problem, right? But this time I'm going to go against the previously defined polarities of Vx and Vout. Okay, so we're going to go round this way for I1 this time.
Just a quick question.
Yep, what's up?
So to find VO, it's just I2 times R5.
Sorry, I keep forgetting about that. You are perfectly correct, right? So in this case, I didn't answer the question. That'll teach me, right? So we actually want to find V out, and as you said, it's going to be, because the polarity is all the same, V out is just R5 times R2. So R5 times I2 rather, and let's just work that out, what that is in Matlab. R5 is 4700 and I2 is, so let's just put that on the screen so you can see what I'm doing. A1 and it's I2, so it's the second row and it's the third column, and then we need to multiply that by 4700. So it's minus 1.319 to 4 significant figures. Volts. Okay, and that's the thing that was asked for. Thank you. I should have gone through the whole question. Okay, so let's try it again, but this time we'll make R2, VR2, the opposite polarity of Vx. Right, so I've chosen my current, my mesh current here, so we've got a plus, a minus, and now VR2 has got to be that way to satisfy the passive sign convention. Right, and then let's make I2 again go into the negative of V out, so VR5 is the negative of V out. Okay, so there's our polarities and our directions, and then we can say, okay, let's go through the voltage source first. So minus 12, right? We're going into the minus side of VS1, plus VR3, plus VR2, plus VR1 equals 0. And let's just keep going with this one for a little bit. So it's minus 12, VR3. Now we've still got I1 going in the same direction as I2 through R3, so the total current through R3 is I1 plus I2. So that's plus 4700, I1 plus I2. Okay, and then plus 2200, I1. I1. And then plus 6800, I1, and then we're back to the beginning, so that's equal to 0. So then what do we get? We get 4700, 6900. Did I do the addition wrong in the other one? Oh no, I probably got it right. 6900 plus 6800 is 13700, I1. 13700 I1. Okay, and then plus 4700 I2, and this time equals 12. And then on this side, we're going into the positive side of VS2, so it's 5Vx plus VR3 plus VR4 plus VR5 equals 0. So 5Vx, 5 times Vx. Now Vx, this is where the problems start cropping up. Vx is now equal to minus VR2, right? Which is equal to minus 2200 I1. You've got to be very careful with polarities once you start ignoring or having to ignore the marked polarities on the circuit. Okay, so there's the first one. Then VR3 is 4700, and again we've got I1 plus I2, and let's just keep scrolling across. 4700 plus 8100 I2 plus 4700 I2 equals 0. And what does that come out to be? That comes out to be 11,000 I1 plus 4700 I1, which is what, 16,700 I1, is that right? And then we've got 12,800 16,800, 17,500. Equals 0. Now I just gotta check.
Isn't 5 times 2200, that's negative, and then...
Oh, you're right. You're right. I was reading this. You are perfectly correct. I was reading this as -5, but it's not. There's a...
That confused me too. I was like, why is it both -5 and negative 2200?
Right. Thank you very much. I screwed up there. I was wondering why it was so big. It should be... Right, now it's better. Sorry about that. Okay, so now it's minus 11,000, right? And then plus 4,700. So what's that? That goes to minus 7,000 and minus 6,300. That's more like it. Okay. And excuse me. Now we get pretty much, well, very similar matrix equation to what we had before, right? So it's 13,700, 4,700, minus 6,300, 1,750, 17,500, 12 and 0. Okay, let's just check that against this one. Looks exactly the same, except the 12 is negated. And what that's going to do is probably change our polarities of our currents. So mesh 2, let's just... Ooh. So mesh 2 is exactly the same as what we had before, but except that that's a plus sign, right? I think that's right. Let's just type it out. 3,700, 13,700, 4,700, 12 minus 6,300, 17,500. It looks good. So then we can do A2 equals RF mesh 2. And again, I'm going to just access that last column so I can see more significant figures. And that looks pretty similar to what we got before, except the signs have changed. Right, so our I1 and I2 are now equal to 0.7794, and oops, whoa, what happened there? My tricky setup went kablooey. Oh well, let me just I'm hoping I'm still videoing okay, yeah?
Yeah, it's fine.
Okay, yeah, sorry, my tricky extra setup is, I wanted to be able to see the video that's going out on a separate screen, and I was using a tablet as the separate screen, but its battery just died. So the screen that was on there is came back and to my main computer screens and moved everything around immediately. Okay, so where did Matlab go? Let's grab Matlab again. I can't do it there. So that's 7794 and 2807. And again, they're in milliamps. I think that's what we got before. Yeah, except they're negated, right? So as you would expect, because we chose the currents going in the opposite direction, this gives us the same answer. It's just one of them's a negative, the other due to the direction change. Now let's have a look at what the V out is, right? So V out, and again remember the polarities are different. So V out is equal to minus VR5, which is equal to minus I2 times R5, which is going to be 4700. Well, minus 4700 times 0.2807. And that's going to be, I think that's the same as the numbers we got before. Yep. So again, it's going to be, and I can't draw it there on black. So that's going to be equal to the number we got before, minus 1.319 volts. Minus 0.319. Let's erase that and draw it a bit better. In fact, why don't we just draw it in white? Okay, so the tricky bit about going against the polarities here, one of them is this piece, that Vx is equal to minus VR2, and the other tricky bit is this piece, that V out is minus VR5. And it all works, it's just you have to be careful with the signs and the polarity.
So I have a quick question.
Yep, go for it.
So when it comes to like the signs of the currents, my understanding is they're pretty much meaningless unless you have drawn the directions. But then when it comes to the voltage, the sign is doesn't matter what directions you assign the currents to be. Is that right?
When it comes, can you repeat that?
For example, if you were to give us the circuit and ask us what the currents are, the sign of the current can be either negative or positive, and that depends on how we define the direction.
That's correct.
But the voltage is always going to be the same sign no matter how we solve it. Is that right?
Well, remember once you've defined the current direction, that effectively also defines the polarity on the resistors, because the resistors have to satisfy the passive sign convention, right? So you'll notice here on R1 the positive is at the top and the negative is at the bottom, but on R2, because I chose I1 going in the other direction, now the polarity is on the positive, is on the bottom, and the negative is at the top. Okay, it effectively, to ensure that the resistors satisfy the passive sign convention, your choice of current direction will determine what the polarity of those voltages are. Does that answer the question?
Yeah, it does. Thanks.
Yeah. Okay. Okay, so this question didn't really deal with the super mesh issue, but I did talk about it briefly right up here. So I'm hoping that I've given you enough information to be able to complete homework 4. Sorry, homework 4. Yeah, so homework 4 is, let's just have a look at homework 4, shall we? Well, oh, it's looked me out. So mesh analysis. Let's actually look at the, let's have a look at my version of it, wherever it's gone. I haven't actually finished it, so, okay, so problem 1. There's nothing fishy about this one, right? So it's a standard mesh analysis problem. So we have 3 KVL equations. There's no current sources, so we don't have to deal with super meshes at all. We don't get any freebies either. Remember, if there's a single mesh current going through a current source, then we've got the answer immediately. And then the systems of equations, right? Be careful with some of these questions. Just give you ohms. Some of these questions give you kilo ohms in the resistor value. So just be careful that you've got the right scale. Okay, so I1 is going minus 14 volts plus VR1. VR1 is R1, which is 9 times I1 minus I3, right? That's that one. And then VR2, and this is sort of answering the question we had earlier, right? These are the only variables in this question are the currents. We've already specified what the voltages are, and the way WebWork works, there are no VR2, VR1, VR3, VR4 variables. It's just the mesh currents that we're interested in as the unknowns. And then R2 is 6 ohms, so the VR2 is 6 times I1, and I2 is going in the opposite direction through R2, so it's 6 times I1 minus I2. The I2 one, we have V2 is 10 volts, so it's plus 10. And then it's R3, which is 9 times I2, that's VR3. VR2 is again, this time the other way around, 6 times I2 minus I1, because we're looking at it from the perspective of I2. And then I3, we're going into the negative side of V2, and then it's 9 times I3 minus I1. Again, it's the negative because we're looking at it now in terms of from the perspective of I3, and then R4 is 5 ohms, so, and there's nothing else going through it except I3, so it's 5I3. And you can do these, right? You can do these whichever way around you want. I could put that around there, and it should still give me the right right, and it even says this answer is equivalent to the one you just submitted. Okay, and then it asks to solve the equations, and basically we've got to rearrange these into an RF format. Right, so it's going to be 15. Let's see if we can do that. I don't know. I'll only do the one. Right, so it's the first is going to be 15 I1 and minus 6 I2, and then I3 is minus 9, and there's a 14 volts, and then is minus 6 I1, and how many? 15 I2 and no I3s, and then the 10 has to be negated because it's got to be on the other side for our equation to work, so it's minus 10, and then it's minus 9 I1 by the looks of things, and no I2, and how many I3? 14 I3, and then we take the 10 over the other side, so it's positive 10. Right, so let's just have a look at that. I think that looks about right. Right, and then we can just do RF mesh 3, and they're the answers that I got. Looks like I only did them to 4 significant figures, but there are, well, the top and bottom ones here have 5 significant figures. And this is what I was saying right here, that really is 14 volts, but you don't want to put in a V there, right? But contrary wise here, the answer is individual currents, and in the mesh analysis, in the nodal analysis homework, it'll be individual voltages, so you need to give the units. Here it's amperes, and in the other one it's volts. And again here the answer is V out, and it gives us in voltage. Okay, so that's that one. Let's have a look at this one. Okay, so types of equations. Well, we've got a current source, so we can't form a KVL equation for I2. So we've got to do a KCL equation. Excuse me. And the KCL equation for I2 is just is just I2 equals 0.0007 in amps, right? That's 700 microamps. And the KVL for I1 is minus Vs, so it's minus 13, plus 6,000 I1 plus 8,000. Now here, remember, you've got that K in front of all of these, so that's multiplied by 1,000 plus 8,000 times, what's that going to be? I1 minus I2. And that equals 0. And let's just check our answers. Yeah, so I got those two right. And then solving, well, we've already solved for I2, so we can just cut and paste that there. And then I1, we're going to have to rearrange this and get it. I'll leave it as an exercise, because I do want to try and get through, just have a quick look at all the problems. The next problem, problem 3.
Professor, for the previous problem, what would be the output voltage?
What?
Or how can we calculate the output voltage on problem number 2?
Okay. Well, that's a good question. Let me copy that image so I can draw on it back over here. Right, so this is mesh analysis. So let's just paste that here. Okay, so even though the this is a current source and we don't know what V out is, we can still write a KVL equation for I2, right? So we can say KVL for I2 is going to be VR2 plus VR3 plus V out equals 0. Okay, from the point of view of I2. So V out is equal to minus VR2 minus VR3. And VR minus VR2 is minus R2 times I2 minus I1. Right? And then minus VR3 is minus I2 R3. Okay, and that's that.
Can't see what you're writing because it's kind of covered.
Sorry.
Can you explain again, please?
So, you can. Kirchhoff's voltage law still holds, right? The only reason we can't write a mesh equation, or we can't use the Kirchhoff's voltage law equation to do mesh analysis when there's a current source is because we don't know what V out is. So we use KCL instead, right? Once we've solved for I1 and I2, then we know all the voltages. We know VR2, we know VR1, we know VR3. So I can still write out that same Kirchhoff's voltage law equation, right? I'm going around the loop. I'm going around the loop this way. And I have, right, this is VR2 from the point of view of I2, this is VR3. So I can still go around and say, okay, it's VR2 plus VR3 and I'm going into the positive side of V out. Right? So I can this equation I can still write out. It's just when I first write it out, before I've solved the problem, I don't know what V out is. And I don't know what VR3 is and I don't know what VR2 is. But now that I've solved for VR2 and VR3, I can still write the equation. And there's only one now. By the time I've solved for I1 and I2, the only unknown now is V out. And I can just rearrange the equation to get an expression for V out in terms of what I do know. And that's the way to get the answer for the final the final box. Does that help?
Yes.
Yeah? Okay, good. Right, so well, let's I want to take a break shortly, but let's just finish this problem and then I'll continue after the break. So so what did I say? This is problem 2. Oh, and it's because I didn't submit the answers. Oh well. So in this case, I2 is just equal to 0.0007, and the KVL equation for I1, as I said, is going to be round minus 13 plus 8,000 I1 plus no, 6,000, sorry. 6,000 I1 is R1 plus 8,000 times I1 minus I2. Let's just submit those answers. Check we got it right. Oh, I didn't put an equal 0 at the end. Okay, so now everything's correct. And now I need to solve for I1 and I2. I've already solved for I2, but I've got to give it the units now. And let's just do some math over here. Right, so that means that it's what's that, 14,000 I1 equals 13 plus 8,000 times 0.0007. So I1 is equal to 13 plus 8,000 times 0.0007 divided by 14,000. And now where's my trusty Matlab gone? And so I1 equals 13 plus 8,000 times 0.0007 divided by 14,000. And I'm just going to multiply that by 1,000 so I can see more significant figures. I should be able to, should I format long? Yeah, that's better. Okay, so now I can just write out, was that 1.329 to 4 significant figures. And that's milliamps. So let's try 1.329. And I think it recognizes that. Let's just check my answers. No, it doesn't like milliamps for some reason. Don't you hate that? Okay, so now everything is correct. And now let's figure out what where's it gone? There it is. Right, so our there's our V out. So let's plug that into Matlab. Right, so V out equals, and I've forgotten which what R2 is. R2 is 8,000. So R2 is minus 8,000 times I2, which is 0.0007, minus I1, which is 0.001329, minus I2, which is 0.0007, times, and I've forgotten what R3 is. R3 is 9,000. Right, so it's minus 1.268 volts. Okay, and we're all good. So I'm just going to quickly skim through the next, but we'll go through the other questions after the break. So, as I said, this is a super mesh problem. Problem 4 is also a super mesh problem. And problem 5 is a super mesh problem. So lots of super mesh problems, okay, because of those two mesh currents flowing through the current sources. Okay, so does anybody have any questions so far about what we've been doing?
I just want to point out, for the homework, if you do end up changing the unlimited attempts thing, then you can always hit like preview my answers, and before part 4, it won't give you an attempt, and it'll still move you on to the next phase. I realized that when doing the homework.
Sorry, can you say that again?
So like if you're on part 1 and you want to check your answer, you can hit preview my answers, and it'll move you on to the next stage if it's correct.
Oh, okay. That's kind of interesting.
But it doesn't work on part 4. So you can basically, go through it with one attempt until you get to the last part if you didn't have unlimited attempts.
Yeah, I in this particular case, sorry, I prefer having unlimited attempts, right? I get, that it why you might limit it, but in this class I don't.
Thank you.
Okay, no
I'm
worries.
just pointing it out, but yeah, thanks.
Yeah, no problem. That's good information for everybody else. Okay, so I will go through some of those, not in as much detail, but I will maybe at least do the first couple of sections of each question. But let's have a 10-minute break for now, and I'll see you back in about 10 minutes. Okay, let's go back, and we've done problem 2, so let's have a look at problem 3. And I won't do all of these, but I'll try and answer any questions that you have. Right. So, as I said, there's this current source in the way, so we can't write a KVL equation for I1, and we can't write a KVL equation for I2. But we can write a KCL equation for I1, I2 minus I1 equals IS. Right? IS and I2 are going in the same direction through the current source. So I2 equals I1 plus IS. So normally we would have when we've got 3 meshes, we have 3 unknowns, so we'd need 3 equations. We still need 3 equations, but normally there'd be 3 KVL equations, but in this case we probably need, we'll have 1 fewer KVL equation, and we need a KCL equation. So then we can check answers. Okay, and they're good. And then we get this option, and let me just copy that image so I can draw on it. Okay, so the KCL equation, let's just write that one down. That one is just IS, but we know what IS is. It's 4IX. Ooh, this could be tricky, right? There's IX there. So we might have IX is equal to I1 minus I3. So IS is equal to 4 times I1 minus I3. Yeah, and then that's IS. So what I was, let's just start from the beginning. What I was trying to start with is IS equals I2 minus I1. The trouble is we don't have an actual value for IS. We don't have a current number. We've just, because it's a dependent source. It's in the diamond rather than in the circle. So and the number or the information we're given is 4IX. IX is the current flowing through R2. So that means IX is equal to I1, which is going in the same direction as IX, minus I3, which is going in the opposite direction. So I think that means we need to have 4 times I1 minus I3. And let's just check our answers there. Yeah, it seems to think that one's correct, although it's reorganized it for me. That's all right. Now the I3 equation, let's have a look at that one. Well, that's just going to be I3 times R4, which is 9, plus VR3, which is 9 times, and it's going to be I3 minus I2, and then plus VR2, and that's again 9 times I3 minus I1 this time, and that whole thing equals 0 because it's a KVL equation. Okay, so that's that. And now the tricky bit is the super KVL. It's not that tricky, but it's a bit different from the standard, right? So what we've got to do for the super KVL, right? Super KVL, or the super mesh, is we've got to combine the I1 mesh and the I2 mesh, but avoid passing through the current source. So we can just do this, right? We can go around this way. Okay, and that's our super KVL. That should be an L, not a V. Let's just erase that. Okay, super KVL. And then what does that tell us? Well, that tells us that we have VS, right, because we're going through there, plus VR1 plus VR2 plus VR3 equals 0. And I've forgotten what all those numbers are, so let me just see if I can put that up on my other screen so I can read the numbers off. Right, so VS is 11 volts, and then VR1 is just I1. Right, remember, we've still got to have the polarities of each of our passive devices satisfy the passive sign convention, right? So that's the way that is. So VR1 is just R1, which is 8 ohms times I1. VR2, R2 is 9, so that's 9 times, and that's going to be I1 minus I3. And then VR3, R3 is also 9, is going to be 9 times I2 minus I3, and that equals 0. Okay, and I'm just going to try and type that in exactly the way I've written it. So 11 plus 8 I1 plus 9 times I1 minus I3, and I didn't do a plus, I did an underscore, which is wrong. 9 plus 9 times I2 minus I3, and that equals 0. Okay, so I've just typed that in there. There's an 11 plus 8I1 plus 9 times I1 minus I3 plus 9 times I2 minus I3. And hopefully that's right. Thinking about it? Yep. And again, it's reorganized it for me, which is kind of nice of it. So I'm going to submit those answers so far. And now let's just write out what the see if we can write out what the RF is for this. Right, so it's going to be 17, 9, minus 18, minus 11, 5, minus 1, minus 4, 0, 20, ooh, hold it. That's in a different order, isn't it? Got to be careful there. That's minus 9. Minus 9. 27, 0. Okay, and that should tell us what if we plug that into RF, we should get our values. Okay, so there's mesh 3. Did I type it in right? Looks like I did. Let's make it A3 equals RF mesh 3. Oh well, that's, you can tell they're probably the right answer because there's only 2 significant figures that are non-zero, at least in I2, and only 1 in the other 2, right? So let's just plug those in, see if that gives us the right numbers. So minus 0.7, minus 1.1, and minus 0.6. Oh, it doesn't have units. Doh. Okay, and then what's the last one? What's IX? Right, so IX is going to be I1 minus I3. That was what we said before. Right, so I1 minus I3, so it's going to be minus 0.1 amps. And we've got it all right. I actually didn't mean to go through that whole one, so let's. I won't do that for the next one. I'll just have a quick look at it. I've already gone through this one, right? So we've got 1 and 1. There's only 2 meshes to start with, and there's only one current source, and they're both going through it. So we need to have one KVL and one KCL. And so the KCL equation is going to be IS equals I2 minus I1. Well, but we've got to give the value of IS, right? It's 3.5 volts. And then the super mesh is probably going to go around that way. And we've got minus 16 volts for our VS. R1 is 3, so that's 3I1. That's R1. And that's R3. Right, VR3. And then also R4. And then R2 is the last one. And that sums to 0. Okay, that should be pretty straightforward. And then here we've got 3 meshes, but there's 2 of them sharing a current source. So again, we've got to do our 2 and 1. And again, we get a super KVL, a KCL. Let's have a look at the KCL equation, right? So IS, which is 5, is equal to I1 minus I2. I2 is going in the wrong direction. And then let's just have a quick look at what that means here. Okay, so for this one, the super KVL has to use I1 and I2 and avoid IS. So we probably want to go around like this. Okay, so it's going to be VR3 plus VR2 plus VR1 minus V1 equals 0. And then the KVL equation for I3 should be pretty straightforward. It's just VR1 plus VR2 plus V2 equals 0, although V2 is a dependent source. Right, so we need to figure out what V out is. Let's have a look at what V out is. Well, V out is equal to it's going in the right direction, the right polarity for I3, so it's going to be R2 times I3 minus I2. Okay, whatever R2 was, R2 is 6 ohms. Okay, and then again, that's partly why I like web work. It's clear that what it's asking for is the final answer, whereas if I give you this same sort of problem in just a paper format, you do what I did in the earlier question, and I forget to answer what V out is. Right, but at least here it's obvious that there's something else you have to do because of the way it's set up. Okay, any questions about any of that?
One last question. In problem 4, where is the output voltage located in the schematic?
Find the output voltage. That's a good question. Right, it's called VR3 in this example.
Oh, okay, I see. Thank you.
Okay, normally it'd be V out, right, or VO, but in this particular example it's labeled differently and it's called VR3. Yeah, good question. It does change from all the others. Okay, so let's leave mesh analysis there for now. And there goes my dog. My dog dislikes other dogs, and she's also decided. There's a neighbour of mine across the road, and the neighbour has funnily enough, has a chimney on the house, and there's 2 turkey vultures that have decided to roost on the chimney, and my dog can see the 2 turkey vultures from where she usually sits, and she doesn't like turkey vultures. So she usually. This morning I couldn't quite figure out what she was on about, and then I realised the turkey vultures were back. So, although I suspect that's a dog at the moment. Okay, sorry about that. nodal analysis. So let's just wind all the way back and remember what nodal analysis does, right? Where mesh analysis does KVL, nodal analysis looks at KCL. Where mesh analysis looks at mesh currents, nodal analysis looks at node voltages. Okay, so the steps are almost identical except for the swapping between node and mesh and voltage and current. Right? Identify the nodes. Express the element currents as functions of the node voltage. Apply KCL, Kirchhoff's current law, at each of the nodes except the reference node. Distribute and group like terms, plug in the values, and solve the system. Okay, that's pretty straightforward. And I'm not going to solve any of these ones, but right, you can see the node voltages. What I am going to do is have a look at some of these other ones, right? And I'm just going to go through examples. So here we have a circuit, and even though I'm drawing the nodes as dots, it means all of the wires connected to those dots is the node, right? The node is an area of constant voltage, so it's not a point. Okay, so that was step one, identify the nodes. And I've forgotten what step two was. Step two, express the element currents. Okay, so there's element currents. So the element currents, and you have to define the directions you mean, right? So here I'm going to say IR1, and just like with defining the directions of the mesh currents, defining the directions of the element currents is completely arbitrary. You can choose whichever way you like. I have a habit of choosing the mesh current direction, the element current directions to be so that there's at least one node where all of the element currents flow into that node only, right? So I tend, for this sort of circuit, I tend to define things like that. You don't have to. You can define them, like I said, it's completely arbitrary. You can define them going in the opposite direction of the three I've done, or one of them in the opposite direction. Some people, for example, prefer having current flow down like that for this one. And that's okay, that works, provided you stick to that definition of current direction. Right, and then go ahead.
A quick question. So if you have like IR1 going to the right and IR2 going upwards, doesn't that mess with Kirchhoff's voltage law, because shouldn't still that law apply where the current all goes clockwise in one mesh?
It does still apply, right? And the difference will be whereas when we do mesh analysis and we choose our mesh current to go, let me just change color, and we choose our mesh current to go around like that, for example, the thing with that is the polarities of the volt of VR1 and VR2 are consistent, right? The trouble is now I'm choosing them different polarities, right? So it should still work. It's just now I've got to, you wouldn't want to do KVL analysis this way, right? Because you'd have to be very careful that you've got the signs all right. That's why we choose mesh currents for mesh analysis and make sure that everything's flowing. Whereas the nodal analysis, KCL, which is where we're headed, provided, again, we are consistent with our choice of current directions in each of the elements, KVL should still work. It still applies. It's a law, right? You can't go against the law. I don't know whether that answers the question. Maybe what we should do is, once we're a little bit further along, we should revisit. Once we've got some numbers for this, we should revisit it and just check that it all works out. Okay?
Yeah, that answers my question, because like you said, it's kind of arbitrary where you define the directions. It just, yeah, it makes sense though.
Okay. But I'll try and remember to revisit the question once we've got some numbers. Okay, so there our, and let me just finish off the, so that's got a plus and that's got a minus. Okay, so IR1 is flowing from A to B, right? So it's VA minus VB on 6, and IR2. Now, this one's a little tricky because it's flowing from 0 to B, so it's 0 minus VB on 12. And then IR3 is flowing from C to B, so it's VC minus VB on 12. So they're the currents, and so the next step is to apply KCL at the nodes, right? So at A, right, we get IS minus IR1, because IS is flowing into the node and IR1 is flowing out of the node, equals 0. Or IR1 equals IS, right, if you want to write it that way. At B, and remember I chose my current element current directions explicitly to be able to write all of these in a positive manner, right? It's IR1 plus IR2 plus IR3 equals 0. And then at C, we can't write a KCL equation, but we've got a freebie, because there's a single voltage source connecting from the reference node to the node C, so we can just write down directly that VC equals 8 volts. Okay, so let me just see if I can, I probably shouldn't have written those there. So let's do this. Let's combine these two equations and say that IS plus IR2 plus IR3 equals 0. Doesn't really matter. We can do it that way. So minus VB on 12, so that's 2/3 minus VB on 12 for IR2, and then plus VC minus VB on 12, plus VC minus VB on VB. Why am I writing I? On 12 equals 0. Okay, and then I can probably write IR1, right, which is VA minus VB on 6, VA minus VB on 6 equals 2/3. Now, I already know that VC is 8 volts, right? So I can replace that. It's no longer an unknown. And because of the way I could have written this as VA minus VB on 6, and then I'd have two equations in two unknowns. I still got two equations in two unknowns, but this equation, the first one I wrote down, only has one unknown in it, now that I know what VC is. So that makes it a little easier to solve. I don't actually need to write a matrix equation to solve this one. I can just solve it.
Is that a VC minus VB in that expression? Or
here?
Yeah.
Yeah, that's VC minus VB. And we already know that VC is 8 volts. Okay? And then what do? So that's going to be minus VB on 12 minus another VB on 12, and that equals minus 2/3, and then that's going to be minus 8 on 12, which is probably also 2/3. Maybe not. Okay, so that's minus VB on 6, right? 2/12 of VB, and that equals 2/3, and that's 2/3, so it's minus 4 on 3. Multiply both sides by minus 6, right? So it's 24 on 3, which is 8 volts. Okay, and then we can substitute that back up into here. We get VA minus 8 on 6 equals 2/3. So what's that? That's multiply both sides by 6, and we get VA minus 8 equals 4. Well, VA is 12 volts. Okay, so what we've got is VA is 12 volts, and then both VB and VC are 8 volts.
Can you move the screen back over? I can't see that last part of the VA VB that you just stopped.
Sorry, I've just got
Yeah, that part right.
I've just got Matlab in the road. so I can't see what I'm showing you. So yeah, is that what you wanted?
Yeah.
Okay, so let's think about KVL now, Kirchhoff's voltage law. So one interesting thing about this problem is that VC minus VB equals 0, right? Because VC and VB are equal. So 8 volt, if let's go round the loop. Oh, let's go round the loop that way. Right, so we've got minus 8 volts plus 0 volts, and then that's going to be another well, because we're going that way, it's got to be a plus 8 volts, right? Because we're going against the way we defined IR2. Okay, so that one gets us. We have a slight problem over here in doing KVL because we've got this current source, so we don't know what that's going to be. So it's just going to end up being well, we know it's 12 volts, right? We've got the value there. And then it's 12, 4, and 8, right? So that ends up being the right run around, or the right value. We've got 12, which is composed of 4 volts, which is the drop across R1, and then another 8 volt drop across R2. So rising 12 volts over IS, and then dropping 8 and 4. So we still meet KVL, we still satisfy KVL, but it's because we're defining now element currents rather than mesh currents, we've got to be very tricky with the polarities. Okay, so I tend to try and avoid combining nodal analysis and mesh analysis simply because that does tend, the difference between mesh currents and element currents can get tricky. We could have defined, as I said earlier, we could have defined IR2 in the same direction effectively, right? So then it'd be less confusing. Again, my preference for nodal analysis is to try and find one node to make all of the element currents flow into. You don't have to. It just means when you do the KCL equation, the element currents that flow out of the node are negative, right? Because flowing out of the node is the negative of flowing into the node. Okay? And then I think I briefly talked about this last week, but I didn't actually solve the problem. So I'm gonna solve the problem this time. And let me we might as well talk it through, right? So the problem with this one, this is a super node problem. And the reason it's a super node problem is because we now have a voltage source, Vs, that's connected between two non-reference nodes. It's connected between node B and node C, and the reference node is the earth or the zero reference, which is the one down the bottom. If the voltage source, like in our previous example, is connected between the reference and another node, that's a freebie, right? We immediately get what the voltage is. But when the voltage source is connected between two of the other nodes, not involving the reference node, then we have the super node version of super mesh, right? The nodal analysis version of super mesh, which is called a super node. And rather than being able to, in this example, rather than being able to find 4 KCL equations, we have to replace 2 of the KCL equations with a super KCL equation and a KVL equation. Okay, and in this case, the effectively what happens is we combine nodes B and C, and the KVL equation we get is, because of the polarity of Vs, is Vc minus Vb equals Vs, right? So that's where we get Vc minus Vb. And then when we consider KCL, we effectively make everything in that box. Let me just, we make everything in this box into a huge node, a super node. And we just think about the currents flowing into that super node. And it's true, right? Any, if you have a circuit and you partition off a part of that circuit, KCL still has to apply. If it didn't apply, then you'd be producing current out of nowhere. So let's have a look, right? So the first step in nodal analysis was identify the nodes. We've already done that here. We've got nodes A, B, and C. Next is to write the element currents. And the elements are here. So I think I've already drawn most of them, but let's draw these ones as well. Okay, so then IR1 is equal to 0 minus VA on 3. IR2 is equal to VA minus VB because of the direction I've chosen on 6. IR3, again because of the direction I've chosen, is going to be just VB on 12. IR4 is going to be VC on 4. Yeah, is there a question? And IR5 is going to be VC minus VD on 8. And IR6 is bucking the trend, and that's going to be 0 minus VD on 5. Okay, so they're all of our element currents, and now we've got to write KCL at the nodes, right? But we've got 3 nodes, two normal nodes at A and D, and then a supernode where we've combined B and C into a supernode. So let's start at A. At A, we've got IR1 minus IR2 equals 0. At BC, or the supernode, we've got IR2 minus IR3 minus IR4 minus IR5 equals 0. And then at D, we have IR5 plus IR6 equals 0, because they're both flowing into the node at D. Okay, so let's write that out again. So IR1, so that becomes minus VA on 3, and IR2 is VA minus VB on 6, so minus VA minus VB on 6 equals 0. And let's just do this one again, this one. So IR2 is again VA minus VB on 6 minus VR3, which is VB on 12. It should be a B, make it look like one maybe. And then minus IR4 minus VC on 4. And sorry, what am I doing? And then IR5, which is VC minus VD on 8, and we're subtracting it. Minus VC minus VD on 8, and that equals 0. And then the last one, we get IR5 plus IR6, so it's VC minus VD on 8 plus, but it's going to be minus VD on 5, because the expression for IR6 is effectively negative. Okay, we can combine that with our KVL equation up here, and we now have 4 equations. 1, 2, 3, 3, and then 4. Right, we have 4 equations in 4 unknowns. So let's write them out. I'm going to go back to writing it out in full matrix form, just so we can see what's happening, and I hope I've left myself enough room. I've got 4, maybe I haven't, VB, VC, and VD. Right, our first one, VC minus VB, and the coefficients are 1 and minus 1. Right, so we have 0 VAs, 1 VB, minus 1 VC, and 0 VDs, and then the constant is 8. So for 2, we've got, let me just, what do we got? We got minus a third, minus a sixth, VA, plus a sixth VB. Right, and there's no VC or VD. And minus a third minus a sixth, that's minus 2/6 minus 1/6, so that's minus 3/6 or minus a half VA. I might just make my pencil a bit thinner so I can fit it in. And then 1/6 VB, and no VC and no VD, and no constant. Okay, and then we're here. What have we got? What does that become? That's a bit bigger, isn't it? It's got everybody. It's got 1/6 of VA and minus 1/6 and minus 1/12 of VB. So that's 3/12 or minus 1/4 VB, I think. And VC, there's minus 1/4 minus 1/8, so that's minus 3/8 VC. It should be an 8. And then what? VD. So it's going to be plus 1/8 of VD equals 0. So let's see if we can put that in. So that's 1/6 minus 1/4 minus 3/8 and plus 1/8. And then the last one, that's no VAs, no VBs, 1/8 of VD, or VC rather, and then minus, what's that, 5/40 plus 8/40 plus 13/40.
Can you show us the full equation that you're working on? Like, show more to the left, where it came from.
Is that one, this one here? So it's IR5 plus IR6. And that's VC minus VD on 8 minus VD on 5. Is that okay? And then I probably should have... that's actually a minus. Right, and that's VD. Let's just make that go up a bit. And that equals 0. I should have put an equals 0 in there too. Does that show you enough? Yeah? Okay, so then we've got no VAs, no VBs, we've got 1/8 of a VC, and we've got minus 13 on 40. I hope I got that right. Right, because it's minus 1/8 and minus 1/5. Easiest way to add those up is to change it into 40ths. So 1/8 is 5/40, and 1/5 is 8/40. So it's minus 5 minus 8/40, which is minus 13/40. So I think that's right. Oh, and I've been forgetting to fill out the zeros, but there's only zeros in the rest of these elements here. Okay, and then we can go back to Matlab and see about and we've got 0, 1, minus 1, 0, 8, minus a half, 1/6, 0, 0, 1, I think that's a sixth, minus 1/4, minus 3/8, 1/8, and then 0, 0, 1/8, and oops, I forgot to put the 0 in. So it's an 8. I forgot to put the 0 in there. And I forgot to put the 0 in there. And then 1/8 minus 13 40ths, and then another 0. Hopefully that works out. Yeah, it's a bit, might be because I'm using format long. Let's go with format short. Okay, so there's the, ooh, I think that's right. And then I can just do RF of nodal 1. And there I get some voltages. 1.672, 5.016, minus 2.984, and minus 1.148. So let's just write those out. Okay, so we've got, so that ends up being (1.672) to 4 significant figures, 5.016 to 4, minus 2.984 to 4, and minus 1.148 to 4, and they're all in volts. Okay, let's just have a look at the negative ones. The negative ones are VC and VD. Ooh, did I get that right? VD is negative. I don't think that should be right.
Professor, I think you have your first row of the matrix backwards. It should be -1 and then +1, I think.
Oh, you're right. You're right. Thank you. That makes sense. Thank you for that. So let's just bring Matlab back and try and correct that. It's gone away again. For some reason, okay, so I should have had -1 on the first one, right? And +1 there. Okay, and then RF nodal 1, and now we get something maybe a bit more sensible. Ooh, is that right? So what did let me correct myself over here. So it's just the signs by the looks of things. So I'll correct these. So those signs disappear, minus signs disappear, and we've got a minus here and a minus here. So let's just see what that says. Right, so it says that what was it? VA and VB are negative. Right, and that sort of makes sense, right? You've got VA here, so that's the most negative number. I can look at it. Actually, no, it's not. It's not going to be the most negative. This is going to be the most negative here, on the negative side of the voltage source, right? And it's because this voltage source is not connected on either side of it to the reference, right? So it's sort of floating around, and what actual voltages at node B and node C reference to 0 is going to be dependent on all the currents that we've just figured out. Right, so what we've just figured out is that the voltage here is minus 1.672, and the voltage here is minus 5.016. The voltage here is 2.984, and the voltage here is 1.148. And I think that sort of makes sense because of the way the voltage source is not connected to the reference. And just a quick sanity check, right? Just check that the voltage difference between nodes B and C are 8 volts, and it looks like it is, at least within our significant figures. Everybody okay with that? Okay. So let's have a look at a more complicated problem. Okay, this is a more complicated problem for a couple of reasons. The main reason being it doesn't have any voltage sources. It's only got current sources. The other reason is one of those current sources is a dependent source. So let's have a look. And again, we'll go through the algorithm. So first up, we have defined the nodes. So the nodes, what's the best way to label these? Let's go with node A. And let's go with node B. And let's go with node C. And then everything else is either part of one of those nodes or the reference node. And define the element currents. Right, and because of the way I out is going, I'm just going to define that as IR1. And I can't, maybe I can do it over here, but just for simplicity's sake, I'm going to do this and this, right? So they're all flowing in the same direction. And again, just for simplicity's sake, I'm going to select my IR4 to go that way. So they're my element currents, and now I need to write down what they are in terms of the node voltages. IR1 is equal to VA on 8. IR2 is equal to VB on 2. IR3 is equal to VC on 4. And IR4 is equal to VA minus VC divided by 1. So it's just VA minus VC. And then we've got a rough...
IR... Alright, is IR3... Oh, never mind, I had my nodes mixed up. Never mind.
Okay, yeah, I mean, this one's a little challenging because the node is actually quite large, right? This is all of node C. So, but even though I draw it as a dot. Okay, so that's that. So the next thing is to KCL everything, right? So let's look at A to start with. A, we've got, well, everything's flowing out of node A. We've got minus 4 amps IS1, minus IR4, which is VA minus VC, minus IR1, which is VA on 8, and that equals 0. At B, we have 4 amps flowing in. We've got minus IR2, which is VC on 4. And we've got minus 2I out, right? 2I out. I out is equal to IR1, right? So we can say minus 2 times VA on 8. And then that all equals 0. And then at C, what do we got? We've got IR4.
I think you did a mistake.
Yeah, what did I do wrong?
So at node B, shouldn't it be VB over 2?
VB over 2. You are correct. Sorry about that. Right, so I don't know why I said VC on 4. That's just wrong. So wrong. So IR2 is VB on 2. You're right. Thank you. But it's flowing out of the node, so it's VB on 2. Okay? And then node C. What do we do with node C? We've got IR4, which is VA minus VC, and it's flowing in, so it's positive. We've got 2I0 flowing in, so it's positive, so it's twice VA on 8. And we've got IR3 flowing out, so that's minus VC on 4. And it's just those three, so that equals 0. Okay, so we have 3 equations, we have 3 unknowns. We just need to manipulate them a little bit so that we can get them into some semblance of order. So let's just rearrange. So remember the fourth step is distribute and group like terms, so let's do that. So here we've got minus 9/8 VA minus VC equals 4. And here, well, there's not much to do there really, is there? It's just minus VB on 2 minus VA on 4 equals minus 4. And here we've got VA, actually, and there's, what's that, a quarter, so it's 5/4 of VA, right? And then minus, it looks like it's 5/4 of VC. And that equals 0. I think that makes sense. Please feel free to call out any errors I make. I'm doing this completely unrehearsed, so I do make mistakes. The reason I do that unrehearsed is so that you can see the sorts of mistakes you will make, right? And sometimes I actually make mistakes on purpose. I usually don't, but sometimes I do, just to catch them, just to get you to give me feedback, right? So far, all the mistakes I've made have been real mistakes, so thank you for correcting me. Keep doing it. Okay, so let's write that out in terms of our matrix now, right? So it's, and again, I'll do it in the full matrix form rather than in our quick form, just to so it's minus 9 on 8, 0, minus 1, 4, 0, minus a half, minus a quarter, minus 4, and then 5 on 4, 0, minus 5 on 4, and then a 0. So then I can plug that into Matlab. Hopefully we get a sensible answer. Let's move that over here.
For the first row, shouldn't VC be positive 1 instead of negative 1?
For the first row. Ooh, you are right. Look, I made a mistake all the way back up here, right? Because there's a minus VC. So that one should be positive VC. You're right. And then that means that should be a positive one.
And also on the second row, you flip the VA and the VC terms.
The second row. This in the matrix?
Yes. It should be negative 1/4, negative 1/2, 0, I believe.
You are correct again. Thank you. I am making so many mistakes today. I blame a lack of coffee. Okay, so yeah, that is a VA, and that's. I mean, I need to take my own advice, right? Always try and get the unknowns in the same order in the equation, just because that's the mistake I made. I put VA on the wrong side of VB, so this row should be minus a quarter, minus a half, 0. Yeah, is that correct now?
Yep.
Okay, cool. Thank you. Okay, so I think I just need to plug all of that into Matlab now. Hopefully Matlab will, at least I've figured out how to, oops, where's it gone? I clicked on the wrong thing and it disappeared on me. There we go. So this is Nodal 2. And let's just put that up. So it's minus 9 on 8, 0, 1, 4. I'm going to go to the RF version of the matrix now. Minus a quarter, minus a half, 0, minus 4. And 5 on 4, 0, minus 5 on 4, and then 0. Okay, I think that looks about right. Ooh, look at that. Round numbers. That sounds like it might be correct. So that's so the answer we get out of that is oops, let's make it a bit taller than that. VA, VB, VC equals minus 32, 24, minus 32, and they're all volts. Let's just have a look at what that is. VA and VC are minus 32. So that means IR4 is 0, right? So we've got a minus 32 here. We've got a minus 32 here. And we've got a 24 volts there. Okay. So, both nodal analysis and mesh analysis are pretty similar. One of them, mesh analysis, is just using Kirchhoff's voltage law. Nodal analysis is using Kirchhoff's current law. And they're an algorithm, a sequence of steps that lets you solve complex more complex circuits than you might be able to otherwise. Right? We could probably try and solve all of these circuits using simple series and parallel stuff, but it would take forever. Whereas if we can step up a level and have a look at things from a KCL version in terms of nodal analysis, or a KVL point of view in terms of mesh analysis, then it lets us tackle more complicated problems. Okay, let's just quickly go back to see what we wanted to do today. Okay, so I have reviewed mesh analysis and supermeshes. I've reviewed nodal analysis and supernodes. I think I've talked about homework 4 enough. So I think what we should do next is talk about the lab. Right? Lab 3, which is due today, and Lab 4, I think I should have a look at that, see what it does. Is that okay? So I'll... what do we got? I did want to try and get one of the tutorial questions done, so we should have time. What would you rather do now? Would you rather... okay, let me see if I can I do a poll on that? Is that there? So, no, it didn't like me to do that. Oh no, my poll bot is not working. Why is my poll bot not working? It says it's there. Okay, I don't know why that didn't work the first time. So, what would you rather me talk about, labs or tutorial? Click on the appropriate link and we'll do direct democracy. blue, yes. Okay, so I think people want to look at the labs. So let's do the labs. We got 11 versus 3, so let's go to the labs. Okay, labs it is. And let's see what we got. Well, first of all, for lab 3, does anybody have any questions about... Oh, you want a break? Okay. I forgot about the break. You're right. So when we will have a break, and when we come back, we'll do the labs, and yeah, that'll work. Sorry about that. I get a bit carried away sometimes. So 10-minute break. Thank you, Ryan. And we'll have a quick break, and then we'll come back and look at the labs. Okay, sorry about that. I managed to leave my headset in a bit of a tangle, so it was harder to get back on than normal. Okay, what did we want to do? We wanted to do labs. So let's go back there. And so does anybody have any questions about lab 3, which is due today? Okay,
For the first part 1, it says construct a simple circuit of 5 resistors, and then it says on number 3, design and construct a voltage divider. Are those going to be 2 separate circuits that we're going to screenshot and submit?
That's correct. So let me just walk through what I'm expecting to see. Right. So this is what I'm expecting to see for part 3. Okay, something like that, where you've got a voltage source, and I would expect to see a V out defined here, with the positive side here and the negative side here, and then V out actually is equal to 3.5 volts, and that's equal to R2 divided by R1 plus R2 times 15. Okay, so that's what I'm expecting to see for part 3. For part 1, what does it say? It says a single mesh with at least 5 different resistor values. So, and I think I did that last week, but what I'm expecting to see there is, I don't know, choose your favorite voltage, 10 volts, 15 volts, 1, 2, 3, 4, 5. You don't have to do them in like that. You could do them maybe a bit more sensibly, so that it's not quite as long and thin, and 100 ohms, 200 ohms, 300 ohms, 400 ohms, and just to be buck the trend, 5 ohms, right? Okay, and again here I am expecting to see the mesh defined, mesh current, I. There's only one, so you could call it I1, but I is fine as well. And then that defines your polarities, right? And remember, there's a little bit of an issue as far as how you measure the voltages, and in fact how you measure the currents. You would expect all of the currents for R1, R2, R3, R4 and R5 to be the same, but depending on how you added the resistors to the circuit in LT Spice, you may get them the negative of each other. And the fix is easy. You can just take the element, the resistor, out of circuit, and Control R will rotate the device. Control R twice will effectively flip it 180 degrees. Control R only rotates it by 90 degrees. Okay, and they're the two diagrams I'm expecting. You can just, and please try and only submit a single document. Let's go to the lab, shall we? Oops, it logged me out. So we go to the labs, and if you download that Excel spreadsheet and open it up wherever it got to, it's still thinking about it. basically you should be able to insert any pictures or any other documents that you need into that Excel spreadsheet. Oh, it's gone there. Okay, so let me just do that. Right, so here's the Excel spreadsheet, and I can insert pictures, right? Picture from a file, and I don't know whether that's going to let me do that. This is not from this course, but anyway. Right, so there's a a picture. You can insert it in here. I wondered whether it's possible to insert a PDF. I don't know whether it's possible to do that. That might be harder. See, I think that's only a photo browser. No, sorry, from file is what I want. Picture from file. Oh well, there's a, it's not this course, but there's a PDF document. So you can insert a PDF document in here as well. Now the trouble with that is it only shows in Excel, it only shows you the first page of the PDF. So if you're going to put in PDF documents, I suggest you just make them one page at a time. The reason is because I can see Excel documents within the browser in Blackboard, but if I need to download the the file and open it up in Excel or some other document reader, then that takes me more time, and it means I get less marking done. Right, so generally students want more marking done, you know, provided it's fair and equitable and all that sort of stuff, and gives you good feedback. And I aim to give good feedback. Most of the labs, most of the homework in this course, you should be able to get 100%. Maybe you don't get it on the first try, but you get it on, you know, the second or the third try. I give everybody on both labs and homework 3 tries. And on the web work, obviously, there's infinite number, but hopefully it doesn't take you that many to finish the web work homework. Okay, any questions? Any other questions about lab 3?
So it asks for part 1. It asks for the voltage drop for each of the resistors, and you showed us kind of how to do that, right? Where you drag the measure over the resistor.
That's right. So yeah,
it also asks to measure out the nodes as well.
Right. So there's let me where's LT Spice gone? There it is. So let's just show that. Right. There's 2 different things there that maybe it's gone there. Yes, there it is. No, it's gone away again. Come back. Here you are. Open a recent file. I think that was the one I used. Oh no, that's not the one I used. Let's try again. New schematic. And let's do it so you can see it. Okay, so we want a component, and let's start with the voltage source. That's not a voltage source. That's a voltage source. Right, and let's, I've forgotten, did it say what voltage to use? Let's make it 15, well, 10 volts. I think I used 10 for the first one, didn't I? And then, so there's a sort of a trick you can use. I think it's F2, is that? No, that's not right. It's F3. You can do this. Right, you can make a silly circuit like that, which is a not very interesting circuit, or a circuit that's going to give you lots of current. And then what you can do is you can get a resistor and control R it and just go boom, 2, 3, 4, 5, and we're done, right? And I think I gave it 100. 200, 300, 400, and I think I said 5. Right, and I got to what was is it net name? I always forget. Yeah, the ground. Right, we can put that there and go F3 and connect up the ground. And then I also need a spice directive. And I'm going to use my .tran1. You can use .op in this case. Once we start getting doing sinusoidal voltages, it's better off doing .tran. But for now, .op1 or .tran are fine. Okay, so this is a long-winded answer. Sorry about that. So then the question was, we need to, let's run it. Right, and we get a, let's do that, right? And then we can measure voltage. Now, which is the positive side? Well, let's say that's the positive side. Right, so that's the negative side. So there's one of them. There's the other one. There's the other one. Oops. For some reason, it's decided to... it's not letting me. Why aren't you letting me drag? And that one I can do. For some reason it's those two are too close together for some reason. So I can't get the, so I need to make the space there. But that right, gets most of them. I won't be able to get VR4. Right, so there's our voltages, and then hopefully, now the currents are all facing the wrong way, right? They're all going from right to left, and that's okay. Just provide that. That's why I want you to write down what the currents are. The question was, so how do we get the node voltages? Well, one way to do it is to just go here and click, right? Here and click, here and click. That one, for some reason, it doesn't like it. Here and click. If you just have the red probe on a node and you click, that gets you the voltage between the reference and the node. Whereas if you click and drag, that gets you the voltage between where you clicked and where you dragged to. Okay, so I don't just have to go over a single component, I could go over all the components. And hopefully, it's a bit hard to see, but that's the node up there. It should be 10 volts, funnily enough. Does that, no, that was a stupidly long response to the question, but does that answer the question?
Yes.
Yeah?
Thank you.
You're welcome. Okay, so let me exit full screen and we'll go back to this. So any other questions on Lab 3? That's due this evening at 11:59 p.m. So let's have a look at Lab 4. And this one is to investigate the characteristics of a parallel circuit is the objective. And you want to experimentally verify that the voltage across each is the same, that the sum of the individual branch currents equals the total current, that the reciprocal of the total resistance equals the sum of the reciprocals of the individual branch resistances, that the effect of changing a single resistor value on the total resistance, total current, and distribution, or note that, and then use Kirchhoff's current law to find unknown currents entering a node. Okay, so select 3 different resistances, and we want to draw that up. Construct a simple circuit, measure and calculate the overall resistance of the 3 resistors in parallel. Now, we have a slight problem in that I don't know whether LT Spice can actually measure resistance. Right, so we have to measure the total current and the voltage and use that as the LT Spice measurement. Measure and record all resistances, currents through each resistor and the voltages across. Calculate and record all currents through each resistor and voltages across each resistor. Swap R3 for a different valued resistor and then do the whole thing again. Okay, so the aim is to just make sure you get the right and do I have a... Nope, I don't have it. So let's just run that again. Oh, there it is. So that one I want to exit full screen. That's why it didn't show up. Let's try that again. So run, and then with this one, we want this to the right of the screen. And is that it there? Yeah, there we go. I don't think that's quite what I wanted. Oh, it is. Okay, so let's try that again. Sorry. Let's kill that. Let's kill that and do a completely new schematic. Okay, so this one, let's see if we can save as. This is Lab 4. So we need a voltage source. And let's make it, I don't know, 10 volts. And then what I'm going to do is I'm going to do my wire trick. Like that, and then I'm going to add some resistors. And that one's a bit hard. Okay, and then I need to get my wires back in. and then I need to put my ground in. And F3 to get my wires back. And then 3 different values. So 100, 200, and 300. Okay, so there's the circuit. I think that's what we're after. Where'd it go? Yeah, it looks pretty similar. And we want to measure and calculate the overall resistance. Well, let's do that. So let me just go back here, and then go over here, and we'll put in a page for Lab 4 intro. And I might just insert the printout as well. Now that is the wrong course. Labs. Oh, that's right. I decided to make the labs generic because I do change them a little bit course to course, but okay, so there's our lab, and let's just insert that screenshot that I took. That's a bit small, let's make it a bit bigger. Okay, so there's our circuit, and the first thing you've got to do is let's just close everything up so we've got a bit more screen space. There we go. So the first thing you've got to do is do some calculations. So let's go with R equivalent. Right, remember the thing is R equivalent is equal to 1 on R1. 1 on R equivalent is equal to 1 on R1 plus 1 on R2 plus 1 on R3. Okay, which is 1 on 100 plus 1 on 200 plus 1 on 300. Okay, so R equivalent is 1 on 100 plus 1 on 200 plus 1 on 300. Let's see what Matlab thinks of that. R equivalent is 1 on 100 plus 1 on 200 plus 1 on 300, which is 54.55 ohms. Make sure you get the right units in your reports. Okay, so we've got 10 volts over, so let's call this I total, and let's call each of these I1, I2, and I3. Right? This whole thing up here is a node. Right? It's an area of constant voltage. And KCL says that I total minus I1 minus I2 minus I3 equals 0, or I total equals I1 plus I2 plus I3. Okay, so I total is also equal to V on R equivalent, which is 10 on 54.55. That's volts and that's ohms. Let's see what that comes out to. Right, so it's 183.3 milliamps. And then we got to think about what everything else is, right? So I1 is also equal to V on R, so that's 10 on 100, which is equal to 100 milliamps. I2 is also equal to V on R, which is now 10 on 200 ohms, which is equal to 50 milliamps. And I3 is equal to V on R, 10 on 300, which is going to be 33.3 milliamps. And I hope you can see that adding 100 plus 50 plus 33 gives us 183.3 milliamps. Okay, so that's the calculation part. And you don't have to draw it the way I have. What you do have to draw is the polarities that you're assuming, or the current directions that you're assuming, right? So you do need to somehow indicate that either on a screenshot of the LT spice circuit, or you could draw the whole circuit elsewhere, or you could just draw it on top of the circuit, right? This circuit over here in the PDF. Okay, and then the second piece is to then, this is the calculation. The second part of it is then to run LT Spice and get the measurements, right? And then the third and fourth pieces is to do it again, but replace that with some other number. And I'm using 1, 2, 3, 4, right? It's just a bit brain dead of me, but right. And that's going to equal what, 25 milliamps? So I suspect this is going to be 175 milliamps, right? And I don't know what that is. Let's just do that calculation in Matlab. Right, so we're changing that 300 to a 400, and we can do REQ2, so it's 57.14 for the second part. And the aim is to make sure that all of those numbers tally, that the ones you calculate that I've done here are the ones that LT Spice shows up for you. And where are we going? No, where's LT Spice? There. So I haven't done the Spice directive, so I'm going to do my Spice directive. Trans. I mean, okay. I don't know whether that runs. Is it going to run? No analysis. I should have done tran. So let's edit that. Not trans. and then we can run it. Okay, so there's only one voltage, right? There's only one node up here, so that's my voltage, it's 10 volts. And thankfully all the currents are flowing in the right direction. And it looks like I've got about 100 there, and I've got about 50 there, and I've got about 33 1/3 there. So that all looks right. Oops. There we go. So I just did a Command L on Windows to get the OP output, and obviously I haven't done OP1, so it's not showing me that. Okay, so there's our original one, and then all we need to do is to change that one over to something new. And now we're actually, I've got to stop the run and redo it, don't I, to get the change in the voltage. Remember, you can't change device values during a run. It'll continue to have the same value even if you've changed it. That's why it didn't change to 25 milliamps initially. You have to go and hit stop and then restart it again. That looks about right. Okay, that is pretty much all there is to Lab 4. I'm just going to quickly, just out of my own curiosity, I want to change that one. I'm going to change that to an OP operating point. And no, let's stop it again and start it again and do a voltage, and we've got all the currents. Okay, then just there we go. Right, so now I don't know whether you can see that. I don't know how to change the size of that font, but if you do look at the operating point information, right, it'll tell you all the values of everything, and it does change the value to the ones we did in our calculations. This is just a nice way of getting a quick snapshot of what's on this screen. Sometimes it's a bit hard to read exactly what the different currents and voltages are on the graph, whereas if you do look at the operating point, it'll tell you the numbers in that other window. Right, that one. Oh, and there we go.
How do you get that screen?
So I'm running under macOS, and it's Command L. So I suspect it's Control L under Windows. Let me just see if I can Google the answer. LT Spice. that's it there. I don't know how to show, didn't answer. Does this one show it? Press the run. Doesn't actually say how to get the operating point.
Did it say F3 when you scroll up a little bit more? Was it saying that it'll never mind.
F3.
Right, F3. Yeah, I was thinking maybe there was a shortcut to pull it up.
Well, that I mean, the under Windows, under macOS, it's Command L, and normally under Windows you change the command to Control. Right, but I can't see the. Oh, look, why don't we do this? Let's go. I will try. Let's go and run it on the Citrix server, because that'll be Windows, and that should tell me which one it is.
Yeah, I tried Control L on mine and didn't get anything.
Okay, that's all right. Like I said,
Oh wait, no, actually I did get it. I lied.
You did? So it is Control L?
I believe. Yep.
Okay. Let me just demonstrate it now that I'm halfway there anyway. Hopefully.
Yeah.
Okay, so this is going to be a Windows machine starting up on the Citrix server at CCSU, and hopefully won't take too long. It's thinking about it. Yeah. Okay. And then what do we want? We want LT Spice. There's LT Spice. Ooh, first use. Hopefully it's got all the data it needs. Do I want to say that? I don't know whether I want to say that. No, I don't. Okay, so let's go full screen and file new schematic, and I apologize, so I've got a resistor. Right, so there's some resistors. Now how do I get a voltage source?
If you just right click on the gray part and then go to draft.
Ah, right, then I get the component. Okay, that's that's the same as macOS. There we go. So there we go. And then hopefully it's F3, maybe. It is good. So then I can just do the all that stuff. Connect everything up. Maybe not as prettily as I did it before. And ooh, for some reason it didn't connect those two up. That's not very clever now, is it? So that's that, and then escape, and then I need to is it label net? There we go, to get the ground on there. And then F3 again to connect up the ground. And then I need a spice directive. Right, .op. I think should be enough. And then I think I can hit a run command somewhere. No, there it is. Oh, I've got to give it some numbers. Let's give it some numbers. So that's going to be 10 volts again. Oops. 10 volts. That's going to be, let's go with 100, 200, and 300. Okay, let's see if that runs. And it just popped up automatically because I used the .op command by the looks of things. That's interesting. That's not the way. You see, that's popping up straight away without me having to do anything. But let's just see what happens if I do Control L. It sort of does it, but it doesn't have the operating point. I think, yeah, this seems to be configured to automatically pop it up. Let me just, it's running, so let's see if I can. Oh, I think that might be the difference between running with .op and running with .tran. Let's just try .tran1. Okay, and we'll stop and we'll run, and now when we run we get this, and let's just measure all the currents and measure the voltage. Okay, and then Control L. Control L does now bring this up, but because it doesn't have it, we haven't actually done an operating point analysis. It doesn't have the values that I measured. Okay, so if you use .op as the SPICE directive, you'll automatically get this. It's called an error log. It's not really an error log, but you'll get this log thing popping up under Windows. Whereas the node, all the node information, all the operating point information will already be there. Whereas if you use .tran, it'll use you'll have to use the graph to do the measurements. That help? I learned something about how LT Spice is a little different on both platforms. Okay, that's about all I want to say about Lab 4, unless there are any other questions. Oh, I wish my dog would shut up. I apologise for the noise in the background. We're not going to get to the tutorial because I don't think we've got enough time to go through all of those. So if you can go into the tutorial and have a go at them between now and next week, and next week we might start off going out to the breakout rooms to look at all of those. Okay? Has anybody got any questions? Okay, I'm going to log out of it doesn't let me. Oh, that's because that's up, that's why. I'm going to exit out of that. And let's leave it there. Enjoy the rest of your weekend.
All right. Thank you, Professor.
You're welcome. Thank you.
Thank you.